All right, good morning, guys. We're going to go ahead and do our next lesson today. It's going to be nuclear reactions. It's Module 1, Section 6. This will be the last lesson in this module. So if you haven't already, go ahead and put your phone away and complete the bell ringer in Canvas. Go ahead and pause the video, take care of that, and then come back whenever you're finished. And then, of course, the next step, the mandatory step, by going to joinped.com and using this code up at the top right, go ahead and join this lesson. The code is KGSLKY. So make sure you go to joinpd.com and join the lesson. That's a mandatory step. That way I can monitor your progress, track how you're doing, and give you some feedback as you go along. All right, so there's that. And then finally, get out paper and pencil to write down notes, questions, and to work example problems as we go through the lesson, because the more you write, the more you remember. All right. So again, this is still Module 1, the atom, and finally this is Section 6, which is nuclear reactions. So we're going to talk about two types of nuclear reactions today. And our goal is to be able to compare and contrast those two types, which is nuclear fission and nuclear fusion. All right, and then finally, the second objective, we want to be able to research the use of radioactive elements, which we've kind of already done. You had an assignment in Section 4, which was like the isotope research assignment. So you've kind of already done this before. All right, review vocab. Remember that the mass number is the number after an element's name. So for example, if it says phosphorus 84, then 84 would be the mass number for that isotope of phosphorus. And it represents the sum of its protons and neutrons, so the total number of particles inside of the nucleus of the atom. So carbon-14 would have 14 particles inside of the nucleus, 14 total protons and neutrons. All right, our new vocab for this section, we've got nuclear fission, fusion, and then critical mass, and then finally chain reaction. And here's our main idea. So fission is the splitting of nuclei. So you take one big nucleus and split it into two smaller nucleus. Okay, we're back. Sorry about that. Got somebody walked in here. So anyway, so the main idea was fission is the splitting of nuclei. So you take one big nucleus and it breaks apart into two smaller nuclei. And then fusion is the combining of two nuclei into one. So you take two smaller ones and it forms a bigger nucleus. Okay, so fusion, think of fusing two atoms together. Both of those, they release tremendous amounts of energy. Fission is what happens in like nuclear power plants that is able to generate electricity for like entire cities. Fusion is what happens like in the sun, where it releases all this heat and light that we can see and feel from the earth. All right, so both of those are tremendous amounts of energy. Here's a video. Go ahead and pause this one and open this video in a new tab and watch it. It's from Crash Course. It talks about nuclear chemistry and these reaction types. Very good production quality. Guy does a good job of explaining things. So check this video out and come back whenever you're finished. All right, so let's talk about nuclear reactions and energy. So maybe you've heard of Albert Einstein. Albert Einstein said E equals mc squared. And maybe you've even heard of that equation and possibly don't even know what it means. But here's what it means. So mass and energy are related. E in that equation is energy and m is mass. And so they're related by that equation that Albert Einstein comes up with. Okay. Anytime I lose or gain mass, that's going to be accompanied by a change in energy. All right. So if I have a reaction that loses or gains mass, well, it's going to produce or consume energy that's proportional to the amount of mass that I gained or lost. And the way I can figure out how much is this equation, E equals mc squared, where E represents energy in joules, which is just the SI unit for energy. M is your mass in kilograms, and C is the speed of light. So that's a constant that you can look up, the speed of light. So this is an equation that you would use to determine if I lose or gain a certain amount of mass, how much energy is released. And that video that you just watched kind of goes into a little bit more detail about that equation. Pretty interesting stuff. All right, but most chemical reactions, they produce or consume so little energy that the mass changes are negligible. Negligible just means you can ignore them. They're practically zero. And for our purposes, they will be zero. All right, so most chemical reactions consume so little energy that you can pretty much ignore it. Pretty much ignore any changes in mass. But energy released from nuclear reactions is a ton, so they have significant mass changes. So whenever I have a nuclear reaction, fission or fusion, the energy that is released is so great that it actually you do have to account for the change in mass. Okay, and we talked about these reaction types. So the first one is fission, and fission is the splitting of a nucleus into fragments. So you take one big nucleus and it splits into two, and that is called nuclear fission. And fission releases a lot of energy. Fission is what takes place, like I said, in these power plants, like in Oak Ridge, where we're powering entire cities, generating electricity for everybody in a town and all the businesses and buildings in that town. All right, so fission is accompanied with a very large release of energy. And here's kind of a picture of what it looks like. I've got a big uranium nucleus right there, 235 protons and neutrons inside of its nucleus. And what's going to happen is I'm going to take a neutron, and we have particle accelerators that can just shoot this neutron into this nucleus. And when it does that, it creates something that's very unstable. And remember, things that are unstable want to break apart or release things from its nucleus. So this is going to break apart into two smaller nuclei. It'll break apart into krypton-92 and barium-141, plus it gives off 3 more neutrons and a whole lot of energy. All right, so when this thing breaks apart, it gives off 3 new neutrons that can then be used to knock into 3 more of these uranium atoms and create a big sustainable reaction. All right? So each fission of U-235, uranium-235, releases 2 additional neutrons. Okay, and each of those neutrons can release 2 more neutrons. So if I start with 1 neutron and I hit a uranium-235 atom and it splits and it creates 2 neutrons, then this neutron will hit another atom and this neutron will hit another atom, and each of those will create 2 more neutrons. And you can see how after I get more and more reactions going, I have more and more neutrons to bump into other atoms. So it grows pretty quickly. All right, and this self-sustaining process is called a chain reaction. All right, so it's a chain reaction because all I have to do is get one of them going, and the rest of them just fall into place because the neutrons that are released are able to bump into the other atoms there. Here's a video that shows that chain reaction happening. I guess these are a bunch of uranium-235 atoms, so it's going to show a neutron hitting one and it's splitting, and then it's going to show the neutrons going off in different directions and hitting the others. And eventually, all of these, with just one neutron that I started with, all of these are eventually affected. Okay, and then here's kind of a larger scale demo of this. So you've got a bunch of mouse traps and ping pong balls, and if I just throw one ping pong ball in the ring, then it sets off a chain reaction. One ping pong ball will be affected, it'll bounce up and hit another mouse trap, and then that will bounce up and hit another, and then eventually you've had all the mouse traps get hit. This is a chain reaction kind of on a larger scale. And this is a segment on the Ellen DeGeneres show. So it's kind of entertaining. You can watch that video too. All right, so without sufficient mass, neutrons are able to escape from the sample before starting a chain reaction. So samples with enough mass to sustain a chain reaction are said to have critical mass. So if I don't have enough mass in my starting nucleus to allow neutrons to escape or to allow neutrons to bump into other atoms, then I can't have a chain reaction because I don't have the critical mass required. All right, so you need to have enough mass in order to be able to sustain or keep that chain reaction going. All right, let's talk about nuclear reactors. So nuclear reactors use nuclear fission to produce the energy generated by nuclear reactors. So in a nuclear reactor, you have these fission reactions, these chain reactions going, and each one releases so much energy, and you can harness that energy and use it to power people's homes and businesses and things like that. And the fission within a reactor is started by a neutron-emitting source. Neutron-emitting just means it creates and ejects an electron, and it shoots an electron at something. And you can stop the fission reactor by moving control rods up or down. And so all control rods do is get in between the neutrons and the atom that the neutrons are trying to hit. So if the neutron hits the control rod, it's absorbed into it, and you stop the reaction. If the control rods are up, then the neutron can go right by and hit the next atom and keep the reaction going. All right, so control rods absorb neutrons in the reaction if you want the reaction to stop. All right, so nuclear reactors produce highly radioactive nuclear waste. This is a big problem with nuclear fission, is it creates a lot of waste that is radioactive and harmful to the environment and potentially harmful to people. And so whenever you have radioactive waste like that, some of them have half-lives in the hundreds of years. Some of them are just like a couple weeks. But if you have ones that have long half-lives, they're going to stay around pretty much forever. And so we've got to come up with a way to store these. And so that's a big problem facing chemistry and chemical engineers right now, is how do we store all this radioactive waste that we get from our nuclear reactors? Okay? That's a big issue right now. So here's a video that shows what one of those nuclear reactors looks like and kind of how it operates. So you can watch this one. This is a pretty good one too. It's about maybe a minute or two long. And then watch that one and come back to this one. All right, and here's a picture, again, kind of showing the same thing. So what happens is you have your reactor here. This is where the chemical reaction takes place. And it releases a lot of energy, so it heats up this water that's pumped into the reactor. And when it heats this water up, that water gets pulled back into this reservoir here that's holding more water. And it heats up this water and creates steam, which turns the generator and creates your power, creates your electricity. All right, so the reactor creates very hot stuff. The very hot stuff goes into a container of water. The water boils because it's being heated by the very hot stuff, and the steam goes in and powers the generator. That's the basic setup of a nuclear reactor. This would be designed by somebody like a chemical engineer. So if you're interested in chemical engineering, whenever you graduate and go into college, then maybe this is something that you could design. All right, so here's a little nuclear fission simulation. There's a website on your screen that the Pear Deck will want you to go to and do the simulation. It's on PhET. So you can play around with that and move different atoms around and see if I have more atoms or fewer atoms, how sustainable is the chain reaction. So you can mess around with that simulation there. But we're going to go ahead and talk about the next reaction type, which is nuclear fusion. Okay, so it is possible to, instead of splitting one atom into two, it is possible to take two atoms and combine them into one. So usually whenever you do that, you want to start with two very light elements that have mass numbers less than 60. Okay, and it's just because it's easier to take two small ones and make a little bit bigger one than it is to take two big ones and make really a gigantic one, because nuclei with very, very large numbers of protons and neutrons are very unstable and they won't stick around long. Okay, so the combining of atomic nuclei is called nuclear fusion. Think of it like you're fusing two things together. You're taking two atoms, one here, and you're combining them into one. All right, and nuclear fusion is capable of releasing very large amounts of energy, just like fission. In fact, fusion releases even more energy than fission does. And like I said, this is the reaction that happens like inside of the sun and stars that, you know, gives off that heat and light that we can feel and see from the Earth. Fusion has several advantages over fission. So in a perfect world, if we were able to generate conditions that are good for fusion on Earth at, you know, a cost-effective number, then we would use fusion. But since that's very difficult to achieve, we have to use fission on Earth because we just don't have the technology or the capacity to do nuclear fusion on a large scale. All right, so with nuclear fusion, some of the advantages: lightweight isotopes are abundant. There are a lot more of the elements like 1 through 30 on the periodic table floating around than there are of the larger elements that are required for nuclear fission. So just the supply of elements that we could use for fusion is much, much greater. It's just more accessible. Fusion products are not radioactive. So if we can run nuclear fusion reactions, the products that they create are stable, and we don't have to worry about nuclear waste and storing them and harming the environment. It's just a lot cleaner. Okay, another advantage this is actually a disadvantage. So fusion requires extremely high energies to initiate and sustain a reaction. So in order to even get the reaction started and keep it going, we need to create like extreme temperatures and extreme pressures to keep that reaction alive. We have to really replicate the conditions of the sun on Earth, and that's nearly impossible to do. We can do it, but it's not easy and it's very expensive, and it's just something that doesn't really work for what we need or what we have right now. Okay, so we've got to solve a lot of problems in chemistry before nuclear fusion is a practical source of energy. In a perfect world, fusion would be great. You know, it's cleaner. We've got the materials for it. The only problem is it takes so much energy that we can't sustain nuclear fusion here on Earth. So there's a lot of work to be done in the field of chemistry for nuclear fusion. So if this is something that interests you, pursue nuclear physics or nuclear chemistry a lot further whenever you graduate. All right, so that is it for this lesson. I want you to go ahead and think about this question and answer it. So fusion reactions involve blank. So go ahead and check this out. And whenever you have your answer, go ahead and submit that. I'm going to pause, and then we're going to go ahead and go on to the next one. All right, so if you said B, fusing nuclei together to form larger particles, then great job. So fusion, remember, I'm taking two things and fusing them together to make one thing. All right, that was the last question. So if you want to play around with this nuke map, so nuclear reactions, again, these are the reactions that generate like atomic bombs and things like that. So you can play around with this nuke map and see, you know, different size atomic bombs, and you can even like see how they would affect certain regions of the world. So it's a pretty cool website. It's virtual. You can mess around with that if you want. I recommend it. And then finally, there's some pretty sweet videos. There's this kid named Taylor Wilson who self-taught everything that he knows about like chemistry and nuclear chemistry. He taught himself, and he was like, you know, he was going around to all these different colleges and universities and showing them what he knew, because, you know, whenever he was finished learning and studying, he was really ahead of the field in a lot of the technology that has to do with nuclear fission and nuclear fusion. So check that out. It's a good video. And then a walk around Chernobyl. So maybe you've heard the story of Chernobyl. You probably have. It was a big nuclear reactor meltdown, and it just released a whole lot of radioactive waste into the community and basically made it uninhabitable. So yeah, watch this video about Chernobyl and get an idea for like the power that nuclear reactions actually have. And that is it for this lesson, guys. So thank you for sticking around. Hopefully you got something out of this. If you have any questions, of course, you can message me on any of the platforms that you can communicate with me on. But go ahead and complete the exit ticket. Go ahead and do the assignment for this section, which actually we haven't unlocked yet. So we're going to do this assignment together tomorrow. So don't worry about this assignment for now. There's no homework for this lesson tonight, but we will do the assignment together in class tomorrow. Okay? So again, if you have any questions, let me know. I'm going to go ahead and sign off, and I hope you enjoy the rest of your day.